Greetings mathematicians, welcome to this narrated PowerPoint on functions. Some worked examples. Here I'm going to go through some typical matric function style questions and see how we do them for your all-round mathematical edification. Alright, here's example 1. There it is. Familiarize yourself with that question. There is a graph. Sketched below is the graph of h of x equals a to the power x. That, ladies and gentlemen, is an exponential graph, so it must be this fellow here. There it is. It tells us that a is greater than 0. We know as much because look at the shape of it. R is the y-intercept of h. There it is. The points P and Q lie on h. So there's P and there's Q. So here are our questions. Write down the equation of the asymptote of h. Question B, determine the coordinates of R. Question C, calculate the value of a. Question D, blah, 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 blah. We'll come to that when we get to that. Or as they say in the classics, we'll cross that bridge when we come to it. So, here's question A. Write down the equation of the asymptote of h. Well, given that this is an exponential graph, its asymptote is going to be a horizontal line. And if you recall the format of the equation for this function, it was y equals a to the power of x, which means the asymptote must be at 0. And we can see that from the graph. The asymptote is at 0, so the equation of that asymptote will be y equals 0. Simple as that. Question B. Determine the coordinates of r. Now, r is the y-intercept of our equation. It's the, what am I talking about? It's the y-intercept of our graph. How do you find the y-intercept of any graph? Well, you let the x equal to 0 in the equation. So there's the equation. There it is in its standard form. To find the y-intercept, we let the x equal 0. And it doesn't actually matter that we don't know what a is, because anything to the power 0 is 1. So the y-intercept is 1. Now let's be careful. The question says determine the coordinates of r. So we need to put it in coordinate form. There it is. R is 0 and 1. Yes. Question C. Calculate the value of a. So if you look at our equation, all that we don't know about it is the value of a. How can we work out the value of a? Well, it's simple enough. We take the coordinates of a point that is on the line, such as P, and substitute the x and y coordinates in place of the x and y, the x and y in our equation. So there's our equation. Substitute in the coordinates of P and solve that equation. A must be 3. Now you will remember we have two possible answers for a squared equals 9. It could be 3 or negative 3, but we were told in the question that a is greater than 0, so it must be the positive 3. So that is the answer to that. Right, question D. D is a point such that DP is parallel to the x-axis and DQ is parallel to the y-axis. Determine the length of DP. So this whole question revolves around figuring out what the x-coordinate of D is. Now we've been told that DQ is parallel to the y-axis, which means the x-coordinate at D will be the same as the x-coordinate at Q. But alas, we are not told what the x-coordinate at Q is. We're going to have to work it out. But it's not too much hassle. We take our equation for our exponential graph. There's the graph, there's the equation. We know what the y-coordinate at Q is, so we can substitute that y-coordinate in place of the y here. And that will tell us what the x-coordinate is. So in we go, substitute 1 over 81 in place of the y, and now we have an exponential equation to solve. I'm going to change that 1 over 81 into 3 to the power of negative 4, and that means x must be negative 4. So if this x-coordinate at Q is negative 4, it means the x-coordinate at D must also be negative 4, which means the length of dp is the distance from negative 4 to 2, which means it must be 6 units. There we go. Okay, next question. Question E. Determine the value of k for which the equation h of x plus 2 plus k equals 0 will have a root that is less than negative 6. Okay, settle down, kids. Settle down, kids. See what I did there? Kids, goats, kids. Anyway, okay. This question looks a little bit confusing. So first we're going to look at what does it mean by a root. Well, in this context, a root more or less means an x-intercept. So we're looking for an x-intercept that is less than negative 6. What does all of this mean here? Well, this is a series of translations that has been affected on h of x. There's h of x, and it has been translated. The plus 2 that goes with the x here represents a horizontal translation, in this case to the left by 2 units. And this plus k here represents moving the asymptote up and or down. Right, so I think we can conclude that we're going to have to move this whole graph down if we're going to get any x-intercepts at all, because as it stands, there's no x-intercept, and if we move it up, there still won't be any x-intercepts. So we are going to have to move this graph down to get an x-intercept. Now, before we try and figure out where we're going to get an x-intercept that is less than -6, let's try and figure out where the root will be exactly -6. So if you think about the x-intercept of -6, that is a point where the x-coordinate is -6 and the y-coordinate is 0. So we can substitute that information into our equation. Let's get to our equation first. There's the standard equation for h of x. There it is. We translate it 2 units to the left, and then we move it down. We've established we're moving it down. Right, now we're going to substitute in the points of the x-intercept. Remember the coordinates that I was talking about just now? The coordinates of the x-intercept are going to be an x-coordinate of -6 and a y-coordinate of 0. So I'm going to put a 0 in place of the y and a -6 in place of the x. And in that way, I can figure out what the k will have to be to move this graph down such that it will have a root at exactly -6. So for a root of exactly -6, we substitute that information in. Then what have we got here? Yes, we move then the k from the right-hand side over to the left-hand side where it becomes a negative number. And then -6 plus 2 is -4, so k must be -1/81. So if we make this k here -1/81, then this graph, the translated version of h, will have an x-intercept at exactly -6. I'll repeat that. If we make k there -1/81, then the resulting graph will have an x-intercept or a root at exactly -6. But now we need to think. We want a root that is less than -6. So do we have to move this graph up or down to get a root that is less than -6? Well, let's think about it. If we move this graph really far down, gave it a k of maybe -10, which part of this graph would be the part that is crossing over the x-axis? If I move this graph really far down, all the way down here, then it's going to be the part of the graph somewhere over here where the x-axis gets crossed. If I move it not quite so far down, maybe down to here, then this part of the graph will cross the x-axis. So you can see as we move the graph up, the x-intercept moves to the left. Obviously, if we move it too far up, then it stops having an x-intercept at all. So we know that if my k is -1/81, its x-intercept will be exactly -6. If I move it up from there, the x-intercept will be moving to the left. But I can't move it any higher than 0, because as soon as my k gets to 0, then the asymptote will be 0, which means that there will be no more x-intercept. So my k has to be somewhere bigger than -6. I mean, what am I saying? My k has to be somewhere bigger than -1/81, but less than 0. So for a root less than -6, my k has to be bigger than -1/81, but less than 0. That was a little bit tricky. It's tricky. Question example number 2. We are given this. F of x equals -x/3 and g of x equals log base 2 of x. Write down the equation of g minus 1 of x in the form y equals something. Question B, sketch the graphs of f and x on the same set of axes, clearly showing all intercepts with the axes. Okay, let's have a look at question A first. Right, g to the minus 1 of x, you'll recall, means the inverse function of g. So g is a logarithmic function. We are now told to find the inverse of that. It's not too difficult. First, I'm going to write that in standard form. There it is. And to find the inverse of a function, your first step is always simply to swap the x and the y around. There we go. Then we just have to change the subject of the formula to get the y by itself. And in order to do that, we need to change this from logarithmic form into exponential form. So the 2, which is the base of the log, stays as the base of the exponent, and the x and the y swap around. There we go. Done. That's question A answered. Yes, there's a little red box of glory. Okay, question B. We have to sketch these two graphs. Be careful, we're sketching g of x. We're not sketching the inverse function. We're sketching f of x and g of x on the same set of axes, clearly showing all the intercepts. So, there are two functions that we're sketching. We'll start with f of x because that's a straight line graph. That's easy. The y-intercept is 3, the x-intercept is 3. Right, we'll plot that later, but there's all the information we need to plot that guy. Now let's plot this one. It's often easier, I find, to consider the inverse function first. So our inverse function, which we worked out in question A, is this. And if we think about that, that is an exponential graph. Where is its asymptote? Its asymptote is at 0 because there's no number here. Where is its y-intercept? Well, to find its y-intercept, you make the x equal to 0. 2 to the power 0 is 1. So the y-intercept is going to be at 1. Does it have an x-intercept? No, it doesn't. So let's remember that information. Now, when it comes to plotting this graph, because this is the inverse of that graph, we have to do some swapping of x's and y's around. So the asymptote for this function was y equals 0. The asymptote for the inverse is going to be x equals 0. Likewise, here we had a y-intercept but no x-intercept. For the inverse, we're going to swap that around. We will have no y-intercept, but we will have an x-intercept. And if the y-intercept for this function was 1, the x-intercept for this function will be 1. So we're basically swapping the intercepts around. Now we can get on to plotting it. This that I've drawn here, this green graph, is what this function, the inverse function, would look like. Remember, the inverse function is an exponential graph. What would that look like if I plotted it? Notice that the asymptote is 0, we said so. The y-intercept is at 1. There it is. Now if I was to plot g of x, which is the inverse of this exponential function, it would look something like that. Now do you notice the asymptotes are swapped around? The exponential function's asymptote was the x-axis. Its inverse, the logarithmic function's asymptote, is the y-axis. You notice that this green graph's intercept is on the y-axis at 1. Its inverse's intercept is on the x-axis at 1. So the graph that we were asked to plot was g of x, which is this logarithmic graph here. So there it is. Now we need to plot on our little axes f of x. There it is, straight line, easy. And now we need to put in the coordinates of the intercepts with the axes. There they are. And finally label our graphs. There we go. Not too difficult. You'll often find when you are asked to plot a logarithmic graph, it is easiest to figure out what its exponential inverse would look like and work from there. I certainly find that to be easier. Okie dokie, example number 3, gadzooks, there it is. The diagram shows some graphs. G of x, which is this hyperbola here. Do you recognize the format of a hyperbola? And f of x, which is a logarithmic graph. Are you starting to also recognize what a logarithmic graph looks like? Y equals -1 is the horizontal asymptote of g. There it is. B, point B, 1 and 0, is the x-intercept of f. Point A, t and 1 is the point of intersection between those graphs. And the vertical asymptote of g intersects the x-axis at E. There it is. And the horizontal asymptote at D. And OB is equal to BE. Then there are all the questions. Let's get to them. Write down the range of G. So G of x is the hyperbola. The range refers to the list of all possible y values covered by the graph of G. So this graph, how far down does it go? Well, it goes down to infinity. How far up does it go? Well, it also goes up to infinity. So what are all the possible y values covered by this graph? Well, all of them, except for one, except for the asymptote. So the range is going to be all numbers with the exception of -1. So we write it like this. Y is an element of real numbers, aka all numbers, that we can work with at this stage, except for -1. So there's our answer. Question B. Determine the equation of G. So G of x is our hyperbola. Now we were told in the question that its equation looked like that. So all we have to figure out is the asymptotes. Well, it's not much figuring out because our horizontal asymptote we're told is -1. So Q is the horizontal asymptote. and P is the vertical asymptote. There it is. Now what is that coordinate at E? We are not told what it is, but we are told that OB is equal to BE. So if OB is 1 unit, how did I know it was 1 unit? Well, the x coordinate at B is 1. So if that's 1 and it's the same length as that, then E's x coordinate must be 2. So we can fill in our information there. There's our horizontal asymptote. There's our vertical asymptote. Remember, with our vertical asymptote, we always use the opposite sign. So this x coordinate here was positive 2, so it must be minus 2 in our equation. There we go. Question C, calculate the value of t. Well, t is a point on the hyperbola. So we can substitute in our y coordinate, which we know, substitute it into our equation, and that will work out what the x coordinate is. So there I've substituted the 1, which was the y coordinate from A, in place of the y in our formula, do some mathematics, la-di-da-di-da, and we work out what the x coordinate at A is. So t must be 3. There's our answer. What's the next question? Write down the equation of f to the minus 1 of x in the form y equals something. So f to the minus 1 means the inverse. So we need to write down the equation of the inverse of this logarithmic function. So f of x's equation is this. We need to write down its inverse. So the first step to writing is not die. I'll try not to die from all the coughing. The first step to writing down the inverse to a function is to just swap the x and y around. There they are. Then we have to change the subject of the formula to get y by itself. So we change this from logarithmic form into its exponential form. There we go. Done. That was easy. Right, question E. For which values of x will f to the minus 1 of x be less than 3? Well, f to the minus 1 of x is the inverse function of f, and we've already worked out what its equation is in our previous question. So we need to find out for what values of x will this total up to less than 3. Well, it's going to be easiest to first figure out which values of x make this total up to exactly 3. And the answer is 1. If x is 1, then this totals up to exactly 3. So now for which values of x is this going to total up to less than 3? Well, any number less than 1. There we go. Question F. Determine the point of intersection between f of x and the axis of symmetry of g of x that has a negative gradient. Well, I think first let's try and figure out what is the equation of this axis of symmetry of g that has a negative gradient. So that's going to be that line there. There's the axis of symmetry. There are only 2 axes of symmetry for hyperbola. One that goes this way, one that goes that way. And we are told to use the one that has a negative gradient. So it must be this one. Now, the gradient of all axes of symmetry is either going to be -1 or +1. Because we're working with the one that has a negative gradient, the gradient has to be -1. And it is a straight line, so its format is going to be this. Now all I need to do is work out what my C is. Well, to do that, I'm going to substitute in the coordinates of the point here where the 2 asymptotes cross over, because the axis of symmetry goes through this point. And what are the coordinates here? Well, the x coordinate is 2, we worked it out earlier, and the y coordinate is -1. So I'm going to substitute those in. There we go, and our C must be 1. Therefore, the equation of this axis of symmetry is y equals -x plus 1. Okie dokie. So we're looking for the point of intersection of this graph, the logarithmic function, and this axis of symmetry there. So as always, if I'm trying to find out the point of intersection of 2 functions, I make them equal to each other, like that. Now, it's a bit difficult to try and work with it in this format because we're not very familiar with logs at this stage. So what I'm going to do is change this into its exponential form. The 3 stays the base, but the x and the minus x plus 1 more or less swap sides, and I get this, which you could rewrite like that. All I did is swap the minus x and the 1 around. Now we just use inspection to figure out what does this x have to be so that 3 to the power of that will be equal to that. Well, I think you can figure out that it's 1, because if x here is a 1, 1 minus 1 would be 0, 3 to the power 0 would be 1, and that x is also 1. So the point of intersection then must be when the x-coordinate is 1, which we already know is at this point B here, so the y-coordinate must be 0. And there's our answer. Okay, bye-bye.